Okay, I'm going to do this integral in two ways. The harder way, and then there is an easier way. And I'll give two answers, two different answers, but you'll see that they end up being the same thing in the end. So note that I've called this integral I. I call all my integrals I. It's just handy to call it something. So if you're given a question, an integral to do, I'd start off by saying let I equal this integral, and that way later on in the question you can refer to it by name, and it means that you don't have to copy it out again. So I is the integral of sec squared x times tan x. Alright, so I'm going to start by making a substitution. Now in extension 2 we're generally not told what the substitution is. So we've got to sort of sometimes we've got to experiment and figure that out for ourselves. Generally, it's not too difficult to find. So in this case, I'm going to start off by saying let u equal sec x. All right, so I'm making a substitution. When we make a substitution, we need to change all the terms into that new variable. So u is sec x. Everything in our integral now needs to be in terms of u, and that includes the dx. There now needs to be a du, and so we get that by differentiating sec x. Now sec x is of course 1 on cos x. Okay, so we want to differentiate that. So du dx is equal to so the bottom times the derivative of the top, that'll be 0, minus the top, so minus 1, times the derivative of the bottom, cos x. Now, the derivative of cos x is minus sin x, so minus sin x is just sin x in the top over the bottom squared. Sin x on cos squared x. Now, that's equal to sin x on cos x times 1 on cos x. And so du dx is equal to tan x times sec x. And so du is equal to tan x times sec x dx. Alright, so that is incorporated into this integral. There's a tan x and a sec x in there, so it works out really nicely. So I becomes the integral of, it'll be sec x times tan x. So sec x is u times tan x sec x, which is all du. So this integral turns out quite nice. The integral of u du, and so that's very easy to do. It's just going to be u squared on 2 plus c, and so our integral ends up being sec squared x on 2 plus c. Now I said that there was an easier way to do this, and there is, and often, if you see an integral where you've got a product and part of the product is the derivative of the second part, that makes it quite easy to integrate. In the last one, I made a substitution. I said let u equal sec x. This time, we'll make another substitution, but we'll say let u equal tan x. Alright, so we go through that rigmarole again. So we go du dx equals, this time it's sec squared x, and this is going to work out really nicely. Du is equal to sec squared x dx, and so our integral, I becomes the integral of, again we get u du. And so we integrate that, we're going to get u squared on 2 plus c. And so our answer, weirdly, is tan squared x on 2 plus c. And so you might be thinking, well, how can that be right when our last answer was sec squared x on 2 plus c? That would seem to be wrong. Which one's wrong? One of them can't, they both can't be right. But you need to remember that we've got a Pythagorean identity that links tan squared and sec squared together. We've got, what is it? Tan squared plus 1 equals sec squared x. And you'll note that the only difference between them is that constant. They're very similar. There's only a difference of a constant which separates them, and that constant, of course, could be that one there, plus c. So that constant can be taken up in that c. So tan squared x on 2 plus c really is very minimally different to sec squared x on 2 plus c. The only difference would be the value of the constant. And that's it.